Hello, everybody. Welcome to the LRN 1289 session. This talk will focus on networking patterns that are supported on Oracle Kubernetes Engine. My name is Ajay Chhabria, and I am a solutions architect at Oracle Cloud Infrastructure focused on the Kubernetes service. So we'll start off with a bit of networking foundations recap. So summary of base building block of the OCI networking. If you're already familiar with those base building blocks, it's going to be much easier for you to translate those components into the Kubernetes world. If you're new into the networking, that's going to be a quick introduction to get you on route along with everybody else. Then we'll move on to the cluster connectivity, talking about various gateways we support in Oracle Kubernetes. I will talk about the base building block, the worker node, the pods, and how they communicate using different CNIs. Then we'll talk about more advanced concepts like exposing services, security, and DNS. We're going to spend most of the time in explaining the architectures, traffic flows, and how things are applied together. We won't be doing a lot of how you deploy things. That's something you can look it up. There'll be a few examples, but just expect this to focus primarily on the networking architecture for Oracle Kubernetes. So to start off with the foundations recap, here is an example region, US Ashburn 1. This region has 3 availability domains. Think of it like a physical infrastructure on which you will be deploying your Kubernetes logical components. So the primary logical component here will be your virtual cloud network or your VCN. That is your private environment. Think of it as a virtual private data center. You decide what goes inside of that environment. You decide what that environment communicates with. So the first thing you need to do is decide the IP address block that you allocate to this environment. You would typically use a private IP address block, like the example here is 10.0.0.0/16. Once you decide on the CIDR ranges for your VCN, you can start subdividing them further into subnets. And subnets would be deployed either into a specific availability domain or the entire region across all the 3 availability domains. So a VCN spans the whole region, and so could the subnets as well. Subnets use an IP address block that is a subset of the original VCN CIDR range. Once you have your subnets, you can start deploying Oracle Kubernetes resources into those specific subnets. So in this example, as you can see, the worker nodes have been created into multiple availability domains. There could also be an API endpoint, load balancer, and even pods. All these Kubernetes resources are allocated a private IP address range from their subnets. Now, this VCN is completely isolated. But if we want to connect to, let's say, the internet, we would have to do a few things. So the first thing we would do is we would be deploying an internet gateway, which is a managed gateway in Oracle Cloud Infrastructure. Oracle Cloud Infrastructure, or OCI, supports multiple different types of gateways depending on where you're connecting to. So if you're connecting to the internet, you need an internet gateway. You would also need to allocate a public IPv4 address to the source that is originating the traffic to the internet. In this case, it is a load balancer. So the private IP address, before it leaves for an internet gateway, needs to be translated to this particular public IP address. Once that is done, the next thing you need to do is to set up the routing. So you need to configure a route table that you can associate with any subnets you want to allow the load balancer, in this case, to be able to go out to the internet, or NAT gateway when they're communicating with the internet. So at this point, the load balancer in subnet A, for example, can talk to the internet, but also the internet can initiate the connections to the load balancer. But what about the worker node in subnet B, where we do not want anything from the internet to be able to route to that particular worker node? But we want the worker node to initiate connections outbound, or we need to make the worker node talk to some OCI service. So in this case, we need to deploy another type of gateways that we support in OCI. That could either be a NAT gateway or a service gateway. NAT stands for Network Address Translation. So the NAT gateway here will be translating that private IP address of the worker node to its own public IP address. And NAT gateway would allow the traffic to go out. But if you try to connect to the worker node via the NAT gateway, the traffic will be dropped. So there could also be another situation where a worker node only wants to talk to an OCI service and NAT its traffic. And that is when you can also use something called as the service gateway that will route the traffic through the Oracle backbone and will really not have any footprints over the internet. So the networking connectivity achieved so far through gateways was mainly for north to south traffic. Now let's try to understand how the traffic will move east to west between pods within an OKE cluster. We recently released a new container network interface or a CNI plugin that will provide pods with an IP address from the VCN CIDR, resulting in the same network performance as the virtual machines with no additional overlay required. This is effectively a pod itself or a daemon set of pods that controls how the networking is done. So your pods are routable within your VCN, between your VCN, and with your on-premises network. So in our example here, we have a VCN, we have a worker subnet, we have a worker node, and it would be running the OCI VCN CNI plugin. So once they run the plugin, the pods get an IP address from the VCN CIDR ranges. You can also apply network security groups to those Kubernetes pods. And the pod's IP can also identify the network traffic going in and out of the pods using something called as the VCN flow logs to audit the pod's network traffic that passes through a VCN. So the way we allocate IP address to those pods is we would have a secondary network interface or a VNIC of that particular worker node configured with primary and secondary IP addresses on that particular VNIC. So as pods gets provisioned on the worker node, they would get the IP address allocated from that particular secondary IP address range. That is something the CNI plugin takes care of. And this way, each pod is connected to a VNIC and is directly hooked up to the VCN. Pods are assigned a private IP address from that particular pod subnet. So if we have to look at how pod-to-pod communication looks in this particular scenario, let's add an additional worker node. In this particular worker node, we will also have a secondary VNIC with some secondary IP addresses and a bunch of pods. So if we have two pods that need to communicate, they would use their allocated IP addresses and communicate natively within the VCN. So the pod on the right would actually see the real source IP address of the pod on the left connecting to it. So this is what an OCI VCN CNI plugin works. So this is another CNI we support in OKE called the Flannel CNI. For those who don't know about Flannel, Flannel is a simple and an easy way to configure a layer 3 networking designed for Kubernetes. It runs a small single binary agent called as a flannelD or flannel daemon on each host and is responsible for allocating a subnet lease to each host out of the larger pre-configured address space. So this diagram right here shows how the packet flows between the two pods in two different hosts. So Kubernetes worker nodes run several pods that get their own IP addresses from a private overlay network specific to that particular cluster. So this extra layer you see in yellow of overlay pod network is built using a Flannel CNI plugin that provides the networking at layer 3. So by default, Flannel uses the CIDR block of 10.244.0.0/16 to allocate small subnets with 10.244.x.0/25 mask to each worker node. And pods will use IP addresses from one of these subnets allocate to a given worker node. Flannel uses VXLAN to encapsulate traffic in UDP packets for pod communication in two different hosts. So if your application environment requires you to not use an IP address from the VCN or a high density pod per worker node, then using Flannel CNI is preferable. Another use case related to density per node is VCN IP starvation. So this overlay we saw frees up considerable amount of IPs within the CIDR block if VCN IP starvation is a consideration. Now let's focus on service discovery. Now, when we talk about service discovery in Kubernetes, the first thing to always consider is how we do the DNS resolution, as DNS has been used for service discovery for many years. When we think about how we are incorporating the DNS of the Kubernetes cluster with the DNS of the VCN, it is important to remember that anytime our pods needs to make a DNS call, it's first going to go to the core DNS, which is a service that is running inside the OKE cluster. That core DNS server, if it cannot resolve the request, it will forward that request to the VCN resolver, which is typically an endpoint dedicated for resolving FQDNs inside a VCN. So if the VCN resolver cannot find anything, it will just forward the request to any upstream DNS that you have. Now we think about that, let's actually consider what are some of the domain names that exist and where does the authority exist for each one of those names. So you may be familiar with the VCN resolver. The default names are oraclevcn.com. Now the core DNS and Kubernetes also creates a new authorities that exist like service.cluster.local, and the authority for those remains with the core DNS. So anytime you create a new service inside the Kubernetes, that service name dot namespace name will automatically register inside the core DNS. So if anything does not fit into the service name dot namespace name dot service dot local, then it would be getting forwarded to the VCN resolver. So this is how the service discovery would really work. Now, let's focus on how you would expose your application using the service manifest in Kubernetes. Now, when you define a Kubernetes service and you configure the type load balancer to expose an application to the internet or to a local network, you can specify how the container engine for Kubernetes implements the service of type load balancer. So this configuration you see right here, it would create an OCI load balancer to expose your application as a service. And this is created or this is achieved by creating annotations on top of service, like shown in the above example. And for those who don't know about OCI load balancer, an OCI load balancer is an OSI layer 4 and layer 7 proxy load balancer, which supports features like SSL termination, advanced HTTP routing policies, and it provides the utmost flexibility with responsive scaling up and down. So you choose a custom minimum bandwidth and an optional maximum bandwidth port between 10 Mbps and 8000 Mbps. This is another option you can use to expose your application, where you define the load balancer type to be the network load balancer that will create that NLB for you. And an OCI network load balancer is a non-proxy load balancing solution that performs the pass-through load balancing of OSI layer 3 and layer 4 for workloads. It offers an elastically scalable regional virtual IP address that can scale up or down based on the client traffic with no minimum or maximum bandwidth configuration requirement. It also provides the benefit of flow high availability, source and destination IP address preservation. Now, Within the network load balancer, there are a couple of modes that we support that will define how your external traffic policy would look like. So when you expose your service, you have an option to define the Kubernetes specification called as the external traffic policy that denotes if the client IP should be preserved or not. So let's review the two different modes or architecture for how you can use the network load balancer and the benefits of each. So this is the first mode called as the local mode, which means that if you want to preserve the client IP in the HTTP request, you need to specify the external traffic policy to be local in your service specification. So with this external traffic policy, the proxy rules are configured on a specific node port, let's say somewhere between 30,000 to 32,767, and only for the pods that exist on the same node, or it is local to that particular node, instead of having every pod for a service regardless of where it was placed. So this mode prevents the extra network hop from the cluster mode, but your traffic can potentially become imbalanced if you do not really configure it properly. So with this architecture, you see any ingress traffic must land on the nodes that are running the corresponding ports for that particular service, or the traffic would be dropped. Because the network load balancer is not aware of the pod placement in your Kubernetes cluster, it assumes that each backend or your worker node, Kubernetes node, receives equal distribution of traffic. As you see in this diagram, this assumption can lead to select the pods for an application receiving more traffic than the other pods. Now, the next mode is what we call as the cluster mode. The cluster mode is the default external traffic policy for Kubernetes services. And the assumption here is that you always want to route traffic to all the pods running a service with equal distribution, and preserving a client IP address is not really required. So any request can be sent to any worker node, and Kubernetes handles it getting into the right place. It also results in good load spreading from the load balancer across worker nodes. So when the traffic is routed to a worker node, the worker node routes the traffic back to the pod, which can run on the same node or a different node. So we also support having UDP workloads on the network load balancer. You often need to run non-HTTP based services inside Kubernetes. User Datagram Protocol, or UDP, is a low latency protocol that's ideal for workloads such as real-time streaming, online gaming, and the Internet of Things. So you no longer need to maintain like a fleet of proxy servers in front of your Kubernetes cluster to really ingest the UDP traffic. Instead, you can use a network load balancer for both TCP and UDP traffic. So for example, in this diagram, you can see a gaming enterprise, for example, wants to deploy a UDP-based gaming server and use a network load balancer. So the architecture would be looking like you can have an Oracle Container Engine for Kubernetes or an OKE cluster, and a node pool of Oracle Linux instances, which are powered maybe by ARM-based Oracle processor. And then the UDP game servers would be deployed as an application within the cluster. Then you can also expose a service with the network load balancer. And the game server can also include UDP-based health probe used such as liveness probe. You can have the network load balancer provisioned with the UDP listener and associated with that particular backend set that is running the UDP game server application. And this backend set is configured to register its backend and perform health check on its backends using the UDP protocol. So when the OKE provisions a network load balancer for Kubernetes service of type load balancer, you can define the type of traffic accepted by that listener, specifying the protocol. In this case, as you can see, I've specified the protocol as UDP, on which the listener would accept the connection request. So this is how you would really configure a UDP-based network load balancer. Now, let's focus on how you can bring your own Ingress controller on OKE. So today there are customers that require to use third-party open source Ingress controller that are deployed within their cluster and managed fully by the customer. You can set up different open source Ingress controllers on the OKE you have created with Container Engine for Kubernetes to manage the Kubernetes application traffic. So this diagram right here, it highlights how an Ingress controller looks and operates today on OKE with the bring your own model. So a customer provisions a load balancer service in Kubernetes for the Ingress controller. This Ingress controller is ran on the customer's worker nodes. It receives the request from that particular load balancer and then makes the routing decisions based on Ingress resources you define in Kubernetes. So the Ingress controller routes the traffic to that particular applicable pods. One thing to note here is that the Ingress controller here is acting as both the configurator and the router. And it is, if in case you deploy like an Nginx-based Ingress controller, it would comprise of the Nginx container and sidecar configuration container. So the sample service definition that you see right here has an Ingress class of Nginx that will launch an Nginx-based Ingress controller. And it is also defining the path-based routing that will send all the traffic to a service named Docker Hello World service. So this is like how you can bring your own Ingress controller on to OKE. Now, we recently launched a feature called as Node Label Selector. Now, a load balancer node label selector in OKE helps to map the backend for each service in an Ingress. So let's say if you're using an Ingress, you tend to create multiple services or multiple logical clusters in a single OKE cluster. And each logical cluster or service is exposed to the customer through a load balancer. Now, with more than one load balancer for each service, every load balancer has all the worker nodes hosting the respective Ingress endpoint as the backend. But with node label selectors, you can specify a one-to-one or a one-to-many mapping for those backends of each Ingress load balancer. For example, in this above diagram, you see that the load balancer or a network load balancer you create by exposing a service has only 2 backends instead of 3, but not all the nodes hosting that particular Ingress for that particular service. So this is how you can selectively select the backends for a particular backend set. So let's focus on the security for Kubernetes cluster, which is the last section for this particular talk. Now, when you set up your worker nodes, API endpoint, load balancer, pods, you now have an option to wrap a network security group around the network interface. With NSGs, you can define security rules for those OKE resources independent of the subnet placement. So with the help of NSGs, you can now create an entire OKE cluster within a single subnet, simplifying subnet management altogether. Instead of having separate subnets with different security list rules to control the inbound and outbound traffic for your, let's say, Kubernetes API endpoint, your worker node, pods, and load balancer. Because these different resources would really have varying security requirements. And lastly, I would like to talk about private API endpoints. So we have enterprises requiring robust access control to their Kubernetes cluster to meet their security and compliance needs. So the private API endpoints would really help them to achieve that by providing an option to now assign a private IP address to the API endpoint from that particular VCN. This way, the customers are not really bound to using any public IP address for their particular API endpoint. And the private API endpoint requires fully integrating Kubernetes cluster with the virtual cloud network or the VCN. So in OKE, the cluster worker nodes, the pods, and load balancers are already a part of the VCN, but one can now really also add the Kubernetes API endpoint to the VCN too, making the OKE network more secure. And then you can also use regular VCN routing and firewall rules like network security groups to control access to the Kubernetes API endpoint and make it only accessible either from a corporate network only or via a Bastion host or maybe via specific SaaS services in Oracle. So with that, we have a wrap up. Thank you very much for your time today and have a great day.